Okay, so let's pick up with values. So in quite a lot of definitions of small step evaluation relations, it's quite useful to distinguish between arbitrary programs, or in this case expressions, and values. In other words, um, the things that can sort of represent the final result of a computation. So if you think of this relation, it's quite useful to, as I say here, to think of it as an abstract machine. So an abstract machine is just like a real machine, except it's a software constructed thing. So we can think of this as an abstract machine by saying, well, the state of the machine is always just the term or the program fragment that we're evaluating at the moment. And a step of the machine, in other words, like an instruction step in a real machine, is just some operation that the machine is going to carry out, and the halting states of the abstract machine are those ones where the state says, well, we can't do any more computation at this point. So in the case of the small step relation, we just take the term that we're wanting to evaluate as the starting state, and then we repeatedly use the small step relation to find the next state, and then at some point we find that there aren't any more reductions. In other words, we can't make any more steps, and so the term we're ending up with is the final state of the machine, which is the answer. Now for this particular language, it should be pretty clear that the only things that will be at the end of the computation will be constants. In other words, for constants and pluses just by themselves, we can always evaluate all the way to the end to get a constant. So we call those things values. There might be in some languages that there are other kinds of values, not just constant things. So it might be, we'll see later in the lambda calculus segment in week 12 that functions are values as well, not just numbers. But in this language here, the only kind of value we have is the numbers represented by constant terms like this. So this type of value is like a predicate, if you like, of terms that says is it a value or not, and it only applies if it's a constant. And we can use that to slightly rewrite the evaluation rules. So the previous version looked very similar to this, except for here it said CN or something, right? But we never used the N. We just copied it across to over here. So we can simplify that slightly by saying, well, that the V1 has to be a value, whatever that means. And we know from this definition up here that that's going to cover us for the constants. So that's just a convention that's often used, because it might be that there are bunches of different values, and if you have different kinds of values that you have to get in a particular position, you don't want to have one rule for every form of those. So this lets you abstract away what the values are. And this is the version written in that way of the step relation you see here. This is the difference, is that the value V1 part has been added here, and we're using V1 here as well. So I'm not going to go through it, but you might find it useful to go through and reprove that this particular step relation is deterministic. So we'll use this version from now on, because we want the notion of value for other reasons as we go along. Okay, so if we have this step relation, we might be interested in various properties of it. And one particular property is that we might be interested to know that if we give up an arbitrary program to this relation, then we can evaluate it in all circumstances. Doesn't matter what it is, it's going to evaluate. And one way of expressing that constraint is something called strong progress, which is basically saying either the term we've got is a value, in other words, we've sort of finished evaluating, or there's another term, t prime, such that we can make a step from t to t prime. In other words, we've either got to a value or we can continue to make progress by making steps. And this is a desirable property because we don't want to write a evaluation semantics that somehow gets stuck in the middle, where we get to a thing that's not a value, like it's p something something, but there are no rules that cover making a step from that to something else. And that's the distinction we were making before about big step versus small step. If we get stuck, that's a bad thing. So we want to be able to, in many languages, we want to prove that we can never get stuck. And the program will always be able to be evaluated. So strong progress is one version of that. So I'll skip over the informal version here, but the statement of that is this one, which is saying, well, it doesn't matter which program we have, for all t, t is a value, or there's a t prime that we can step to. Okay, and it's basically proven by an induction on the terms. So we basically just have to consider all the possible kinds of terms. There's only two kinds in this language, which makes it a bit simpler. So if we consider this case, which is the case where the term that we're considering is a constant already, then we can see that this left-hand side holds because Cn is a value. So typically we would just go left and use the value thingy to say, well, that is a value. And if we pick a p, well, we're not going to be able to show this because p's are not values. So we have to go right and somehow show this for the different kinds of things we have. And basically we have to somehow find a term that p, t1, t2 can step to, and we have to use these induction hypotheses to do that. And if you think about this, there's really going to be, it might be that, for example, t1 is already a value, or it might be that t1 can step, and similarly for t2. So let's just look at one level of this a little bit. So if we do inversion on IHT t1, we get two subgoals, right? One for the case where t1 is a value, and another one which you can't see, which is where t1 can step. So if we go into that one, so this is the case where t1 is a value. Now what are the possibilities here? Well, we have to case out what t2 could be. So it might be a value or it might step. So again, we do an inversion and we end up in this situation. So now we're in the sub case where we know both of them are values, which means that we can make some more concrete assumptions about what has to happen here. So if these are both values, they must be constants. So when we do inversion on them, we can find out what the constants are. So it's n and n0. And now we know that this is a way of applying, this is going to be using the plus const rule to get to t prime. So we could use e apply, but also we know what the t prime has to be here, right? So we can instantiate that and then use the plus const to get it. In the other case, I'll just show you how this would work. This is the case where t1 is a constant because it's a value, and t2 can make a step. Don't get confused about the t primes here. There's two different t primes because of this. This 2 exists here. So if we think about what that means, this means this is going to be p, c something, and something that can step. So that's going to be an instance of the +2 rule where we're evaluating the right-hand side because the left-hand side is already evaluated. So we can get the value here. So this is saying get me out to the t prime such that T2 steps to it. And notice that they've renamed this T prime to avoid confusion, because we can't have two T primes in scope. So this one's now called T prime 0. And we know that this must be stepping to P T1, because that's already evaluated, T prime. So we can instantiate that and then use ST plus 2. And then we just have to prove the assumptions, which are that T1 was a value and T2 stepped to T prime. And the last case is very similar to that one. We just did except for the first argument instead of the second argument. Okay, so this is great. Strong progress is quite a powerful property to have of a language. Not all languages have that property. And it leads naturally to this notion of a normal form, which is something that can't be evaluated further, basically. So this is defined for every binary relation on X. Basically starting at T, if there's no T prime that's related to T, then we say T is a normal form. Right? It's sort of the end of the line of this relation. So if you think of a relation as being like arrows in a graph of all the elements of X, you sort of keep following the arrows until there are no more outgoing ones, and then you have a normal form, basically. Now, there's a relationship often between normal forms and values, and for this particular language, we can show, as we will in a minute, that values and normal forms are actually the same thing. In other words, in this language, no matter what you do, if you get to a point where you can't evaluate anymore, the thing you have must be a value. Okay, it's not always the case in a lot of languages, so it's a useful thing to be able to prove. So there's a couple of proofs here which I won't go into detail, but you can see this one is saying if V is a value, then V is a normal form of the step relation. Basically, just goes to, you just have to show that there's no way to make a step from a value to anything. And this one is saying that if you have a normal form, in other words, you can't make a step, then that thing must be a value. In other words, must be a constant. And this is just putting those two things together, both directions. So, as they say here, the thing that's interesting here is that the notion of being a value is just a syntactic thing. It's just saying, well, everything that's a constant is a value. That doesn't necessarily mean that the evaluation semantics, the step relation, is always going to end up in a value. Right? So that's the notion of normal forms. So normal forms are all the places that the evaluation ends up in, and values are a syntactic characterization of certain terms. And this proof for this language at least shows that those two notions coincide. Now the rest of this section is showing you situations where that might not be the case. So temp 1 here, this is a separate module, so this is basically saying, what if we had a different notion of value and step? Or perhaps a different notion of value, perhaps a different notion of step. Does this value, the normal form relationship actually hold? So what's this one about? Well, this one is about that you've got a notion of value that includes the constants, but it also includes any plus that has a value on a constant on the right-hand side. So this is kind of a bogus definition. The step relation is the same, and it turns out that you can prove that values are not the same as normal forms in this in this language. And that's fairly straightforward because this thing, there are terms T1 such that this will be able to make a step, right? So terms of this form won't be normal forms necessarily, but there will be values. So those two notions don't coincide in this case. So I'll let you have a go at proving that if you want to. Temp 2, I think, is a homework exercise. Yes, so I'm asking you to prove it in this case for temp 2. So what's the deal with temp 2? It's got the same value definition as the original one, but it's got a funny step relation part. So this says that if you have a constant, you're allowed to step it to a plus of that constant and 0, which numerically makes some sense, but it sort of ruins the nice properties of the normal forms, because if you think about it, when you get to a constant, it's not the end of the line, because you can make it into a plus and then evaluate the plus to get the constant back, and then evaluate it into a plus, and then so on. So you can just keep evaluating all the way. Okay, so constants now are not normal forms of the step relation, because you can keep evaluating after you get to a constant. So you need to prove this theorem for homework. What about temp 3? So temp 3 is an illustration of the getting stuck idea. So it might be that when you specify the step relation, you don't specify enough rules. You don't specify enough to get you fully evaluating everything. And so in this case, what they've done is they've taken out the step. They've got plus const, they've got plus 1, but they've taken out the plus 2. So there's no rule for plus 2, right? And they've got the same value definition as before. So it should be fairly obvious that there's some terms that are not values. In other words, they're not constants, but they're also normal forms of this relation, because you can get to a point where in the original definition we would want to use the plus 2 step to make some progress, but because plus 2 doesn't exist, we can't use it, and the other two don't apply in the same circumstances as plus 2, so we can't make any steps, which means that the term is a normal form, but it's still a plus, and that's not a value according to this definition. Okay, so temp 4 switches languages, but in a very similar way. Basically says if you've got a term language that's about Booleans, so we have true, we have false, and we have if. And if is a three-way if, right? So the first part is the condition, the second part is the value returned for the then part, and the third is the value returned for the else part. Then we can write similar stepping rules for this language that all sort of talk about how to evaluate ifs, and the values are just true and false in this language. And the same sorts of things can be reasoned about for this language. So I'll let you have a bit of a look at that. But you can prove strong progress for this and determinism for the stepping thing. But the exercise here, small step bool shortcut, is a homework exercise. So the idea is that you might want to extend this Boolean language to have a rule that says that if you've got something like this, where the then and the else branch are the same, there's no point in evaluating the condition, because you're always going to get the same answer. So you can make a single step straight to that value that's in the else and the then and the else branch, without having to go through steps to evaluate this condition. So the exercise that you have to do for homework is to extend the step relation with a rule that gives you this sort of optimized evaluation. And then go on in this exercise down here, properties of altered step, to reason about whether this step relation is still deterministic. You have to say whether it is or not, and you have to prove whichever one of those you say is the case. And also you have to say, does strong progress hold or not, and prove your answer. So those are the 2.2 and 2.3 cases in the homework. Okay, so we'll stop there for now and come back with multi-step reduction.